this, and I'll send the link out later. The thing that we have here is we're going to be looking at section 5.1. And the thing with 5.1 is we're talking about measurement. And basically the idea is going to be this. Now we're going to get into some more specifics about measurement later. We're going to actually look at some measuring devices. And this is going to come up. But the idea is this. If you're making a bunch of measurements, like you're just trying to measure, say, like the dimensions on a box or the dimensions of some kind of cylinder, if you're working on an engine, you're coming up with measurements. If you're doing anything with measurements, there's sort of a basic idea, and it's this. Your collection of measurements used in arithmetic is only as good as your worst measurement. Give you a second to write that down. Your collection of measurements used in arithmetic is only as good as your worst measurement. So this is one of these incentives for whatever you're doing stuff with measurements. You want to do the best you can. And if you're getting some measurements that you're going to use in a formula, say some formula that's going to tell you about volume, something's going to tell you about pressure, the result will only be as good as the worst measurement you have in that formula. And that means that you could do really, really well on taking your measurements, and then there's this one that's just kind of fudged it. That's going to actually govern what kind of answer you get on the other end. So what we're going to do, we're going to talk about significant digits. And you can think of this as a kind of rounding. But what we're doing with it is we're using it to govern how do we use these measurements and base our result on the worst measurement that we have. So let's talk about significant digits. So first off, what are they? The first thing, all non-zero digits are significant. So all non-zero digits are going to be significant. Now, where it gets a little tricky is going to be 0. Because non-zero digits were okay. When 0's in here, we got to be a little careful. So when it appears that it's between two non-zero numbers, So if it's between two non-zero numbers, it is significant. It's also, so let me give an example of this, because with zeros, this is where significance just gets kind of confusing. So let's say we have something like this. This zero is significant. It's also significant when it's on the very right end of a decimal number. So in this case, we mean the presence of a decimal point. So that's on the very right end. Oh, forgot a T. The very right end of a decimal number. So that's going to mean the presence of a decimal point. So for example, 2.0. This zero on the right end is significant. Or let's go 37.120. That's also going to be significant. So those two zeros are going to be significant. Finally, there's a third one where we might kind of force the issue. If the zero has an overbar. See, that's two words, not one word. So if it has an overbar, it's going to be significant. And a place where you're going to see this most likely, because if zero is between two non-zero numbers, it's already significant. You don't need to put an overbar. If it's the right end of a number with a decimal point, like this or this, it's already significant. So what if it's on the right end of a number that doesn't have a decimal point? So say something like this. So that's going to be significant. That has that overbar. So this doesn't have a decimal point. Now there's one more I want to mention. It's sort of a play on the first point. So this is similar to the first point. Though the first point, it's okay if it's between any non-zero numbers, zero is going to be significant. But also, if we've got this overbar, so again, we'll have a replay of what we saw in the first example. But if you have something like this, so again, this is like the first example. Zero is between some non-zero numbers, so it's still significant. But in this case, we have a 0 with an overbar. So this is going to be significant per this rule. And the 0 in between is also going to be significant. So just to kind of point that out, any questions about that? All right. So that's our sort of subsections of the second rule. The third rule is when is 0 not significant? And there's really two situations. We talked about being on the far right of a decimal number. And we mean by decimal, we mean a number with a decimal point. But what if we have a number that doesn't have a decimal point? Say like this, but there's no overbar. Well, if it's to the right, it's on the right end of a whole number, and there's no overbar, that's not going to be significant. So, for example, here. So the far right side of a whole number and no overbar. I'll tack that on there. It's on the far right, but it doesn't have an overbar. So what would that look like? Something like this. This might seem a little confusing. But this is not significant. Neither are these two. They're not significant either. So if we think about this, 0 is significant when it's on the far right of a decimal number, okay? But when you have 400 here, these zeros are significant because this one has an overbar, making it significant. But also this 0 here is now between two significant numbers. Remember, non-zero numbers are significant. So that makes this one significant because it's between two significant digits. So these zeros are going to be significant. But this one is on the far right, so not significant. And this one's between a significant number and a non-significant number. There's nothing that makes this one significant, so it's going to still remain non-significant, or it's going to be non-significant. So any questions about that? All right. So 0 is also not significant when it's on the left end. Here, I'm going to make it a little edit. Let's cross out far here, because this makes it sound like it's only the 1 0. Let's not do that. Let's cross out far. So when else is 0 not significant? Well, it's on the left end of a number. So for example, something like this. These zeros are not significant. And then these zeros are also not significant. Questions about that? So you want to be kind of careful with the zeros. Non-zero numbers, they're automatically significant. A 0 with a bar over it's significant. Any 0 between significant numbers is significant. When you have zeros to the left, or really any number, decimal or not, or to the right of a whole number, then that's where you're going to get non-significant zeros. So any questions about that? We're going to get into some arithmetic. So when we talk about significant figures, we're going to deal with adding, subtracting, and then multiplication, division. And to do those operations, we talk about precision and accuracy. So precision it's the rightmost significant digit. The reason we're going to be interested in this again, oh, sorry, last thing, place value. Don't want to forget that. It's the rightmost significant digit's place value. Now, the reason we're going to be concerned about this is how we're going to govern errors, or not errors really, how well we've made our measurements when we add and subtract those measurements. Precision of those measurements is going to determine what the results will be when we add and subtract. So for example, let's say we have this. Oh, before we do that, we'll do a little bit more. Let's take a look at accuracy and go through the precision and accuracy of the numbers at the same time. So precision is about place value of the rightmost significant digit. Accuracy this is the number of significant digits. So precision is about the place value of the rightmost significant digit. Accuracy is the number of significant digits. And this is going to come into multiplication. And division. But we'll get to that in a bit. So precision is addition and subtraction. Accuracy is multiplication and division. So let's take a look at this. $17.2. So precision is about the place value of the right most significant figure. So for this one, the right most significant figure is a 2, and this is in the tenths place. So it's going to be the tenths for precision. Accuracy, well, these are all non-zero numbers, so the accuracy is going to be 3. So questions about that? Let's see here. Let's try this one. Abbreviate precision and abbreviate accuracy. So what's the precision on this? Well, we've got a 0 on the far right end of our decimal number. So that means these zeros are going to be significant. So this 0 is in the hundreds place. Now, how many significant digits do we have here? Well, the 0 that's on the right of the decimal, that's significant. The 2, it's a non-zero number, so that's also significant. But this 0 is to the left, and that's not significant. The zeros on the left end are not significant. So this has an accuracy of 2. Let's see here. So again, precision, we want to look at the place value of the right most significant digit. Well, we've got an 8, non-zero number. Even if it was a 0, well, got these other zeros here. I think I know the answer to this, but let me double check that one. If these were all zeros, what would you say about that? Let me look that one up. I want to double check that one. But we've got an 8 here. We've got a non-zero number. So we have a tenths, hundredths, thousandths. So this has a precision of thousandths. Now for accuracy, though, how many significant digits do we have? Well, we only have the 1. And then zeros to the left. We have all zeros to the left. There's no other significant digit here that would make all the zeros in between significant. So these aren't going to be significant. There's just the 8. So the accuracy is 1. So what about this one? So in this case, when we talk about precision, we want the right most significant digit. Now, so far with these decimal numbers, it hasn't been too tricky. Maybe it's been a little bit. But if we look to the right, this is a whole number. So zeros on the right of a whole number aren't significant. Not significant, not significant. This one, though, usually wouldn't be significant, but it's got a bar over it. So this is in the thousands. So the precision is the thousands. And then for accuracy, well, it's got a bar, so it's significant. Non-zero, very significant. So this is going to be 3. One more. So again, precision and accuracy. Right, this is a whole number. So the zeros on the right, they're not significant. There's no overbar. So that one's not significant. We got 2 non-zero numbers, and this one's in the tens place. Oh, I'm sorry, this is in the hundreds. Ooh. Apologize for that. It's in the hundreds. Sorry if you were that's your thousands. Sorry about that. So this is the hundreds. That's your ones, your tens, your hundreds. Now for this one, you have our ones and our tens. Now again, accuracy, not significant. Non-zero numbers are significant. Accuracy is going to be 2. So the questions about that. All right. So we're going to talk about the arithmetic. And the way we're going to look at this is when we're adding and subtracting, when we come up with our final answer, we're going to mind precision. So for adding and subtracting. So what we're going to do, again, we're going to look at the precision for the place value of the rightmost significant digit. And what that means is the answer, when we add and subtract, we have to round it to the least precise number. Least precise measurement. Now, there is something I'm going to mention. I'll mention this at the end, but it has to do with what they have are official constants, like legally defined constants. I want to say, I'll double check this. I won't double check this, but you'll find in conversion, say, between metric and the English system. We'll talk about that later. There is one conversion or relationship where it's legally defined. And in that case, even though you might see only, looks like 3 significant digits, you treat it as if it has infinitely many. So we'll talk about that later. Those are special cases. But so let's take a look at this. So for example, so you're adding these 2 numbers. So again, we add them how we've been taught. 6.07, 2.4, Now this we got to be kind of careful. We usually put in a 0 here, but I'm going to put an invisible 0 like this. That is not a significant digit. This is just something we do with the addition. This is the rightmost significant digit, the 4. So we'll add. We have 7, 4, and then 8. So now we got to round this based on significant digits, particularly precision. So 2.4, precision, well, it's going to be the tenths. .07, 6 7/100. Well, there you go. Precision is going to be hundredths. So what this means, we're going to round this to the least, using the least precise number as a guide. And so tenths, that's our least precision. So that means 8/4700. This will become, you're going to round to the tenth spot, 8 5/10. So questions about that? So let's take a look at another one of these. You want to be careful when you're doing this, because when you're making your measurements, because this can really throw things off. Let's say we're adding these 3 numbers. So really precise measurement, really precise measurement. Somebody kind of eyeballed that one. So what can you do? And let's say we're measuring sort of like, say they're even the same object or something similar. And like we're going to compute an average or something. Well, let's see what we get. Let's add these. Now again, this is going to be invisible, and they're not significant. So we'll get 2 here, 7 here, 9 here, 9 here, 12 here, a decimal, carry the 1. We get 7. So we got some really careful measurements, but this one, let's take a look at precision. The precision here is the 1s. This one, tenths, hundreds, thousands, 10,000s, 100,000s, or 100,000s. Really great measurement. Oh. We have 100,000. So the least precise number, of course, is going to be the 1s. So that means this number we're going to round it to 7. And I'm assuming, again, we wanted a similar precision in this measurement than as it was these other twos. But let's say you just kind of said, forget it, let it go. Not interested. Well, what that's going to do, it's going to kind of cancel out the work you did here to some extent. Not maybe completely, but to some extent, you have to have 7. So just sort of an incentive there when you do your measurements, try to hang in there and get those really, really well. So that's going to be addition and subtraction. Let's take a look at multiplication and division. So for this, we're going to round to the least accurate number. Now, so multiplication division, we round to the least accurate number. So remember what accuracy is now. You can take a look at your notes, but what it is the number of significant digits in a number. So let's say we have this. So let's say we have 274 times 32. So again, we do multiplication as before. So 2 times 4 is 8, 14, 4 plus 1 is 5. We use this one, so I'm going to cross it out. 0. 3 times 4 is 12, carry the 1. 3 times 7 is 21, plus 1 is 22. We got this 2 up here. 3 times 2 is 6, plus 2 is 8. So adding these together, 8, 6, 7, and 8. Now, in the past, we would say that this is our answer. But let's take a look at the accuracy. The accuracy here is 3. And for this one, the accuracy is going to be 2. So that means one thing real quick here. Double check. Just being careful. One thing. So that's going to give us 8,800. And the reason we're doing this, we're going to have 2 significant digits because this only has 2 significant digits. Some questions about that? All right. Just want to double check. Here. Let's go with yes. So let's say we have, we've done that one. So we've got multiple multiplications here. And so what we're going to do, just like with the addition, we're going to do all these processes, and then we're going to round at the very end. So let's do 2 times 1, or 2.1 times 1.7. So in this case, 7 times 1, 7. 7 times 2, 14. Put in a 0, 1, 2. And then we'll get 7, 5, and 3. And again, we got to place the decimal. So we want to take the total number of decimal spaces. So the decimal space, decimal space. So 1, 2. That. Well, that's what we get from the multiplication of 2.1 and 1.7. Now we're going to take this 3 and 57 hundredths, multiply by 1.3. 3 times 7 is 1, 21, carry the 2. 3 times 5 is 15, plus 2 is 17, carry the 1. 3 times 3 is 9, plus 1 is 10, and 0. And then I'm going to cross these out again because I've used them. 1 times 7 is 7. 1 times 5 is 5. 1 times 3 is 3. We're going to add it. We'll get 1, 14, carry the 1, 6, and then 4. And again, what we're going to look at, number of decimal spaces. There's 2 in this number and 1 in that number. 1, 2, and 3. So we have an answer, well, a preliminary answer, of 4 and 641 thousandths. But let's take a look at the accuracy of these numbers. So 2.1, and again, we're looking at the number of significant digits. The accuracy is 2. 1.7, the accuracy is again 2. And 1.3, the accuracy again is going to be 2. So what this means is this answer needs to be rounded to 2 significant digits. So 4 and 641 thousandths will become 4 and 6 tenths. So questions about that? Let's see. So another thing that's coming up here, they've got, let me see. So, double check one thing here. There we go. All right. So, just lost my spot. There. So we have this thing. It's sort of a side. This is sort of a, there's a number of different topics they have in this section. They have something called the greatest possible error. And what this is going to be, it's half the precision of a measurement. So, for example, let's say we have, step this back, 14.6 pounds. So for this number, the precision is going to be 6. Or tenths, rather, sorry, tenths. So what that's going to mean is we're going to take the tenths and we're going to represent it sort of in a sort of fundamental decimal form. 1/10. Let me put it this way. 1/10 is 0.1. So what we're going to do, we identify the precision. It's going to be tenths. So we got that. And then a representative of a tenth is 0.1. So when we talk about the greatest possible error, what we're going to do is we're going to take this representative 1/10, we're going to divide it by 2. So I'm going to call it the GPE. Will be 0.1 divided by 2, 0.05. Oh, we'll box this. So what do you do with this? Well, this kind of goes back to tolerance. We saw this earlier, this idea of tolerance. And for our measurement, what we're going to do, let's see. Represent our measurement as 14.6. Let me get the units here right. Plus or minus 0.05. So this is what they mean by greatest possible error, or how we can apply it and put it with our measurement. And so what this means our measurement would be between and so again, sort of like the concept of tolerance. But this is really just as an application of the concept of precision. So I'll do another example with this. Excuse me. Let's say we have something like this. Let's give it some units. We'll call it inches. So first, we want to identify precision. Tenths, hundreds, thousands. It's the place value of the rightmost significant digit. So thousands. So what we're going to look at is 1,000th. And that's going to be this. So our greatest possible error for this measurement will take this representative thousandth divided by 2, and we're going to get 5 10,000ths. So then we're going to represent our measurement 37,014 plus or minus 5 10,000ths. So questions about that? All right. So let's see. So the other thing that comes up in this section is we're going to be looking at units. And what we're going to do is we're going to actually treat units very similarly to numbers. So first off, when we add and subtract the same units, the units in the answer are going to remain the same. So if we add or subtract the same units, then the answer has these same units. So what happens here, so let's say we have this. So let's say we're doing something like this. Well, we're adding and subtracting. Now, if we think about an order of operations, we do adding and subtracting from left to right. So we're going to do the addition first. So we're going to take 16.3 and add it to 8.2. Add our decimal. 3 plus 2 is 5. 6 plus 8 is 14. And then we have 2. And this is still going to be feet. So as long as we're adding and subtracting the same units, we're going to get the same answer here for feet. And then we need to subtract this 2 and 73/100ths, or 2.73. And again, this is all feet. And then for subtraction, I'm going to put this invisible 0 here. That's not a significant digit. So we're going to do this. We can't subtract 3 from 0. So we're going to have to borrow a 1 from the 5. Make that a 4, a 1. So we can do 10 minus 3. 7. But then 4 minus 7, we can't do that either. So we'll borrow 1 from the 4. 14 minus 7 is 7. 3 minus 2 is 1. There we go. So 21 and 77/100ths. Now we've got 4 digits here, but we got to figure out how many significant digits the answer should have. You notice our precision, or our precisions here. So for precision, for adding subtraction, we use precision. So the rightmost significant digit, tenths, hundredths, now the least precise numbers, tenths. So this will become 21 and 8/10. But it's still going to be feet. So when we add and subtract the same units, we get the same units in the end. Where things change is when we multiply and divide. So multiplication and division. Well, what's going to happen here is we're going to treat units like numbers. We're going to treat units like their numbers. So how does this work? Well, what I mean to say is we have inches times inches. So let's say we recall working with numbers. 9 is 2. Let's go with 5 times 5. If you have 5 times 5, you'll get 5 squared. We can represent it as an exponent. Same thing with inches. So we have inches times inches. We're going to get inches squared. Now what they're going to use in the text is they're going to have you write them as square inches. You'll see this. So instead of saying inches squared, you'll see square inches. Now, likewise, let's say we start with square inches. Now, if we take square inches and we divide by inches, well, we can think of this as square inches over inches. The reason being, again, is division and fractions mean the same thing. So square inches is inches times inches over inches. And just like with fractions, we can cancel and reduce. So we can cancel an inches with an inches, and we're going to get inches. So we're going to treat units like their numbers. And you're going to see cancellations like we have in fractions. So let's see, let me pick up an example here. Let's see, where did we go? So let's say we have this. Let's say we drive 100 miles in 2 hours. What is our speed? Now, the way we come up with speed is going to be distance over time. So a little bit of physics here for this problem. Now we are going to mind our significant digits. Now this one, whole number, that means the zeros on the right aren't significant. So just that 1 is the only significant digit. And the number 2, well, there's only one digit, it's non-zero. We got a 2 there, so it's one significant digit. So what that'll do, we're going to take 100 miles divided by 2 hours. And we can divide the 2 into 100. And then we're going to divide the units. So first we're going to divide numbers. And then we're going to divide units. So if we divide the numbers, 100 divided by 2, and 50. And again, significant digits, one significant digit, another significant digit. And when you're doing division, we're thinking about accuracy, which is the number of significant digits. There's 1, there's 1. So it turns out this one has only 1 anyway. There's a 0 on the right, it's not significant. So that's our number. And then we divide our units. Miles divided by hours, well, it's not going to do much. We're just going to get, well, miles divided by hours. And we can represent it as a fraction. So it doesn't really do all that much. But we actually have a special term for this. We have miles over hours. And we call it MPH, miles per hour. And so what we'll get, we put it all together again. So 100 miles over 2 hours is going to be 50 mph. So any questions about that? All right. So let's do this. Let's say we have something like this. And let's say we're measuring the volume of the box. So we're going to come up with the volume where we have, say, a width, a height, and a length. So in this case, again, we're going to multiply left to right. Now, with multiplication, the order actually doesn't matter, but if you want to just be careful, multiplication and division, we always do left to right. Now, division order does matter. You don't want to mix that one up. So again, 6.2, 8.1. 1 times 2 is 2. 1 times 6 is 6. Bring in 0. 8 times 2 is 16. Carry a 1. 8 times 6 is 48. Plus 1 is 49. Double check that. So we get 2, 12, 10, 5. We have 2 decimal spaces, a decimal space here, decimal space here. So our decimal point will go right there. And now we're going to multiply this. 50 and 22 hundredths times 22. So 2 times 2 is 4. 2 times 2 is 4 again. 2 times 0 is 0. 2 times 5 is 10. We'll bring in 0. 2 times 2 is 4, 2 times 2 is 4, 2 times 0 is 0, 2 times 5 is 10. And then decimal spaces, well, we've got 2 decimal spaces. That means we move our decimal point 2 spots. We're going to get that. So we're doing the numbers first. We'll get to the units in a bit. As we do the numbers, we've got, take a look at this, we're multiplying. So we want to talk about accuracy, the number of significant digits. 2 significant digits, 2 significant digits, 2 significant digits. So that means this needs to be rounded. The 2 significant digits. This is what we're going to get. 1100. So we've got our significant digits. We've got the multiplication of our numbers. So what happens here is now I got to do the units. So we have inches times inches times inches. And this is going to be what we might call inches to the 3rd power, inches cubed. Now, there's another abbreviation for this. You'll see this sometimes. Here it is cubic inches. So putting this together, our answer will be 1100 cubic inches. So any questions about that? So let's see, we have about 5 minutes left. There's one thing I want to show you. And it's what we call decimal equivalence. So the idea of decimal equivalence, what you're ultimately trying to do, let me see this. Just going to double check. So what I might do, I might hold back on this. I want to work on a presentation for this one a little bit more precise. So what I might do, yeah, I want to go over this one a little bit more. So what I'll do, I'm going to post a video on this later. I just want to make sure that we spend a little more time on it. We're going to kind of cram it in 5 minutes, and let's not do that. Let's not try to do that at all. So what I'm thinking I'm going to do, I can do a video. I can post a video on this, so at least you have it, so you can work on it on the weekend. And then we'll do that instead. I think that's a better way to go. I will go over it on Tuesday. We have the test on Tuesday. I will go over it on Thursday. But yes, I'll do that. So I'm going to actually hold off right now. So I'll put out the pretest. We'll have that out. I'll get the pretest out tomorrow, solutions by Saturday, and then test on Tuesday. And we're going to be looking at chapters 3 and 4. So if any questions about that, let me know. I'll get out a video for decimal equivalence as soon as possible. So if you want to work on that on the weekend, you can. Though I'd recommend just studying for the test. And so that's going to be it. So that's it for tonight. If any questions, let me know. And well, I'll hear from you soon.